Okay, looks like it's recording. So our first speaker this morning completed his PhD in 2016 at the University of Illinois, Urbana-Champaign under the supervision of Alex Young. His thesis on K-theoretic Schubert calculus won the Philip Tonder Dissertation Prize. He's held positions at Rutgers University and University of Michigan before being hired at University of Waterloo in 2020. Oliver Pechenik will speak on the Castelnuovo-Mumford regularity of matrix Schubert varieties. Thank you very much, Oliver. Go ahead.
Thanks, Mike. So I've been to a few of these CAAC meetings now, and they're always a great time. So it's really exciting to be invited to speak at one. Let me share my screen again. All right, how's that? Can we see? Looks good. Okay, so this is really going to be a combinatorial algebra meets algebraic combinatorics talk. The question we're looking at is entirely a question of commutative algebra. Looks like a commutative algebra problem, but the solution is going to involve only combinatorics. So hopefully both communities will be reasonably happy. So if you've been here all weekend, you might feel like you've already seen this talk. So let me do a quick compare and contrast with Colleen's talk from a couple of days ago. You'll see the title is very similar, and we have this co-author and a Wygant in common, but it's not the same talk. So first of all, we've swapped in David Speyer for Jenna Rajchgot, and second of all, we have different theorems, I promise. So we're still going to be studying matrix Schubert varieties, like have shown up a lot this week. And we're going to be computing Castelnuovo-Mumford regularity, but whereas Colleen, so our results are both more general and also less general. So on the one hand, Colleen was not studying all matrix Schubert varieties, she was just studying ones that were vexillary, right? Some subclass of matrix Schubert varieties. We're going to study all of them. But on the other hand, Colleen was talking about more general things, Castelnuovo-Lustig varieties and stuff. And so we're not going to touch on any of that. I will never say the word Castelnuovo-Lustig again. So we're just going to think explicitly about matrix Schubert varieties. And also, our formula is going to look very different, right? Hers is something diagrammatic, and ours is going to be something with words, I guess. Okay, and Anna's here today, so I think I saw her in the audience. So maybe if you have questions in the chat, maybe she will tend to them. That would be great. Okay, so here's a sort of slide about the flag variety, which maybe we don't need at this point in the weekend. But let's think about it a little bit anyway. So as a set, my complete flag variety is just a set of all ways of nesting vector subspaces inside each other, one in each dimension. And so that's just some set, but I can topologize it, because if I think about how the general linear group acts on Cn, all it's doing is just moving the vectors around. But actually, it doesn't just move vectors around, it actually moves flags. If I have a nested collection of subspaces and I act by GLN, that moves that flag to another flag, and the action is transitive. So that means that I have this one-to-one correspondence between elements of my set, elements of my complete flag variety, and cosets of GLN modulo the stabilizer of my favorite flag. And if you're like me, here's my favorite flag. Right here, the one that just sort of initial segments, spans of initial coordinate vectors. Okay, and so if you think a little bit what the stabilizer of that's going to be, it's going to be upper triangular matrices. And so the experts in the audience are expecting U here to stand for unipotent, but U does not stand for unipotent, U stands for upper, and it's just my Borel. Okay. So there's my flag variety. Now, when I don't know about other people learning linear algebra, when I first learned linear algebra, like the first thing you do is you do a lot of Gaussian elimination, a lot of row reduction, and it all boils down to taking some kind of matrix, presumably in GLN, and well, you're trying to put it in triangular form. So you're trying to find this upper triangular matrix associated to it, and the row reductions you're doing are just in the form of, factoring off this lower triangular matrix. So you're writing your matrix as something lower times something upper, and you're doing this LU decomposition. And most of the time, of course, you can do that, but occasionally it doesn't work out. Occasionally you have to swap some of the rows around. You have to permute some of the rows before you can actually obtain this LU decomposition. So we get this decomposition of the entire general linear group into these pieces according to how complicated of a row swap did you need to do in order to do your Gaussian elimination. So I can factor every matrix as LU with some particular permutation matrix stuck in the middle. Okay, so there's this nice decomposition of GLN. If I look down, I said that my flag variety was a quotient of GLN, so I can just map this decomposition down on the GLN, project it down, and I get something really nice. I get these Schubert cells, and they're beautiful. So what's nice about them is that they are topologically just affine spaces, and their closures give a nice cell decomposition, actually a cell decomposition into complex cells. And from that, you can just read off all sorts of nice geometric topological data about your flag variety. Okay, so we want to understand Schubert varieties. That's where I come from. But Fulton noticed that, in fact, these Schubert varieties, which are a little bit complicated, have nice affine models that you can look at. So what he says is, well, let me take this decomposition of GLN, and instead of mapping it down onto the flag variety and closing it, why don't I just leave it where it is? Why don't I just close it right in place inside the space of all n by n matrices? And it's not clear this is going to be so helpful, but it really is. I get this matrix Schubert variety, which is somehow analogous to a Schubert variety, which knows a lot of things about Schubert varieties, but it is just some affine variety, and it's cut out very concretely by a bunch of determinants. Okay, so I'm not going to tell you exactly which ones, but at this point in the weekend, you've seen several times which rank conditions we're imposing and where. Okay, so these are the objects we're going to study. We're going to study these matrix Schubert varieties. And so they're coming out of the Schubert calculus side of things, but there's like an alternate history of the world in which they could have appeared instead from the commutative algebra literature. So various things that were cared about by the commutative algebraists fit inside this story. So classical determinantal ideals, one-sided ladders, they're all inside here. And so the commutative algebraists didn't quite think about this this exact generalization, but it's sort of a very natural thing to do just in terms of having some good ideals to study and play with. They have a lot of nice properties. So the particular property we want to look at for matrix Schubert varieties is this notion of Castelnuovo-Mumford regularity, which is a kind of sort of measure of complexity. So let me try to explain sort of how to think about this. So the setup is we have a polynomial ring, and I have some homogeneous ideal. Okay, and that's my setup. I have my polynomial ring and my n squared matrix coordinates, and I have my ideal. It's homogeneous because it's generated by a bunch of minors. Okay, so I have that thing. And how do I understand the quotient R mod I? Well, a nice way to understand something like that is to have a presentation in terms of generators and relations. But if I have generators and relations, I can understand sort of what's going on. And of course, there's more than one way to write down generators. I could write down lots of sort of superfluous generators, oops. And then I could impose relations saying that I didn't actually need most of them. Okay, so I have some choice there. And I have choice in my relations too. My relations are not independent. I can have relations among my relations. And then I can have relations among those sort of higher order relations as well. Okay, so this free resolution is a way of just encoding all of that data. Over here, I'm going to stick all of my generators. So this direct sum has one summand for every generator. And this value I, these are recording the degrees of my generators. And these B's are just counting how many generators I have of every degree. Okay, so that's some data. And then if I go back to, it's not actually on the screen, but if I go back to this direct sum, right before that, these are where my relations are sitting. I'm going to have one summand for every relation. The i's again are going to be the degrees of my relations, and I'm going to be counting how many relations I have of every degree. And then this keeps going. And you might worry this goes on forever, but you know, Hilbert tells me that in fact this is a finite process. Okay, so this is not unique, of course, because I can, you know, have choices in how many generators I put down, but there's a unique sort of most efficient way of doing this. There's a unique way of making all the counts as small as possible, to using as few polynomials everywhere as you can do. Well, that means that all of these numbers that show up in my free resolution, these numbers as k here, all of these b's, they're all some kind of invariant, some kind of interesting invariant of this ring R mod I. And they must be telling me something about R mod I. And in fact, some of them are telling me very natural geometric information. For example, k here is called the projective dimension of R mod I. And in nice cases, and we're in nice cases, this is telling you something very geometric. It's telling you dimension, or rather codimension. It's telling you the codimension of your space inside the ambient polynomial ring. Okay, so that's very reasonable. Castelnuovo regularity is sort of a orthogonal measure of complexity. So like k here is a measure of complexity in the sense that you would imagine if R mod I is very simple, you can probably resolve it in few steps. If I have to take lots of steps to resolve it, there must be something more complicated going on. So Castelnuovo-Mumford regularity is another measure of how complicated my ring is. I don't know sort of a very geometric way to describe what it's doing, but algebraically it looks quite natural. What we're doing is essentially we're measuring the extent to which we have to use large degree polynomials in this resolution. Right? One way that R mod I could be very simple is if I could do this resolution with only low degree polynomials showing up. If I have to use like a degree 1 million polynomial, there must be something complicated in R mod I forcing that to happen. So remember, these i's are the degrees. So basically, I'm looking for the largest degree that shows up. And this minus j here, right, this is some kind of normalization. Maybe don't worry about it unless you're happy. Okay, so that's what we're doing. We're doing some kind of algebraic complexity measure on these varieties. Okay. So this looks hard to compute. It looks like you have to compute this entire free resolution, which is a very big thing. But we want to sort of get at it in an easier way. So the one trick we have is this ring, R mod I, well, I is homogeneous, so this is a graded ring. And all these graded pieces, you know, degree A homogeneous part, they're all finite dimensional. That means for every number A, I have a corresponding finite dimensional piece, and I can write down its dimension. So I get infinitely many data points. I have this infinite sequence of data. And well, I'm teaching you know, generating functionality this term. And what do you do when you have an infinite sequence of numbers? You build a generating function for them. And in this context, that's called the Hilbert series. So I write down this formal power series here, where the coefficient of this formal variable t to the a is going to be the dimension of my 8th graded piece. And what's really nice when you take this perspective is that although it looked like we had an infinite amount of data, it's actually only finitely much information. So I can always factor out this denominator of 1 minus t to the number of variables. So here it's n squared. And the numerator that I find after I factor, this is just a polynomial. It's called the K-polynomial. Okay, so all that infinite amount of dimension data, it's all really encoded inside this finite polynomial here. And in nice cases, and we're in a very nice case, this K-polynomial doesn't just know all of the dimension information, it also knows things like regularity. So the regularity of the thing we're looking at, we can compute it just as the degree of the K-polynomial minus the projective dimension. So that's just this codimension of my space. Okay, the codimensional matrix Schubert varieties is very well understood. This is very easy. This is just the Coxeter length of the permutation I'm talking about. So I don't need to worry about that. So in terms of the problem at hand, understanding regularity and understanding the degree of K-polynomials are basically the same thing. So we can solve this instead. If I can compute that degree, then I win. Okay. Well, and the advantage here is that these K-polynomials have been studied, in this case, from the algebraic combinatoric side for 4 or 5 decades now, under the name of Grothendieck polynomials. And so Grothendieck polynomials have shown up a couple of times by now. You can compute them with pipe dreams, either with the more classical anti-diagonal pipe dreams or the newer diagonal pipe dreams. I'm not going to tell you that definition. I'll show you instead the original recursive definition. So the recursive definition is like this. Well, first of all, I'm going to tell you for that special permutation that takes a list and writes it in reverse, I'm just going to declare that the Grothendieck polynomial is very simple. It has one term. It's one monomial. It's this particular staircase-shaped monomial. That's all it is. Couldn't really be any simpler than that. And the rest are going to be defined recursively. So anytime I'm looking at my permutation and I see 2 consecutive values like this that are out of order, I can swap them to get a new permutation with those 2 letters in order. And every time I do that, there's a relation between the corresponding Grothendieck polynomials. The Grothendieck polynomials are related by the action of this operator right here, this sort of terrifying operator. So I don't want to get too much into exactly what this operator does, but let's just look at what it does on degrees. So suppose I plug in a homogeneous polynomial into this operator. Well, here's my f. So first I'm going to multiply by 1 minus x I plus 1. So that's going to give me things of the degree I started with, plus things of degree 1 higher. And then over here, I get the same thing, degree I started with, degree 1 higher. And I act by, this is just going to SI swaps some subscripts on my variables. Okay, so in the numerator, I have things of the original degree, things of degree 1 higher. Now I'm dividing by this linear form in the denominator. So I'm going to end up with presumably things of the original degree and things of degree 1 smaller. Okay, so I started with something homogeneous and I've dehomogenized it. And you can imagine now I'm doing this recursively. I'm going to plug in now things that aren't homogeneous probably. They can get like even more unhomogeneous, right? The degrees can spread out in some kind of complicated way. Of course, they might not, right? Things could cancel off some of my degrees. I might end up with nothing left anymore. So a little hard to see what's going on in these polynomials, but they are basically the K-polynomials in weird conventions. If I just take all of my variables and do this linear change of variables, set them all equal to 1 minus t, that just literally is the K-polynomial on the nose. And you can convince yourself that when you do this change of variables, you're not messing with the degree. Right? It might look like things cancel here, but they can't. So the degree of the K-polynomial, the degree of the Grothendieck polynomial, they're literally the same. So all I need to understand are the degrees of these Grothendieck polynomials. I'm going to do a little bit better. I'm not going to study just the degree of it, but let me rip off the entire top degree piece of it. The Grothendieck polynomial, we'll call this the Castelnuovo-Mumford polynomial because it's the part of the Grothendieck polynomial that knows about Castelnuovo-Mumford regularity. And we're going to study that. So they turn out to be quite interesting polynomials. All we really need is the degree, but in fact, there's just a lot of interesting combinatorial structure to these polynomials. You can say a little more about them. And actually, they're probably telling you something about multigraded regularity, but I don't know so much about that story. Okay, so let's move on and see what we can do with this. So, okay, so here's some example of Grothendieck polynomials if you haven't actually seen them. So the point is here's right weak order on the symmetric group S3. S3 is very small, so unfortunately, these Grothendieck polynomials are not quite representative. You'll see most of these are just single monomials and also, of course, homogeneous. This is not really the generic situation. Sort of the only interesting one here is this one. Here I have a degree 1 piece. This is a length 1 permutation. It has only one swap been done to it. So I have this degree 1 piece. This is my Schubert polynomial. And then I have this degree 2 piece. This is my Castelnuovo-Mumford polynomial. And these coincide in all the other cases. So the way you get from like this to this along this arrow is you apply that sort of terrible operator. Okay, so what do we want to notice in this picture? Well, if I just look at the lowest degree piece of these Grothendieck polynomials, so that's just the entire thing in most cases, but it's this piece over here. So I look at these Schubert polynomials, I get 6 different things, right? Every permutation here has a different Schubert polynomial associated to it. But if I look at the top degree pieces, the Castelnuovo-Mumford polynomials, what I see is that this one over here and this one over here, they're actually the same up to a scalar. So instead of getting 6 different Castelnuovo-Mumford polynomials, I only get 5. And this is going to be a general thing that happens. Instead of getting n factorial of these polynomials, I'm going to get Bell numbers of them. They're going to be indexed by set partitions. Okay, so let's see what we can do. Okay, so everything I've told you so far is things I learned from Jenna Rajchgot, unless I told you anything false, in which case I didn't learn that from Jenna. And so she said, okay, so this problem, it really just boils down to understanding this very nice combinatorial question of like, what is the degree of a Grothendieck polynomial? If only I could know that. And so in work she did with Yi Ren and Colleen Robichaud and Avery Saint-Dizier and Anna Wygant, they gave a formula for the case of Grassmannian matrix Schubert varieties. So these are the ones that pull back from Grassmannians. And then in some forthcoming work that Colleen talked about a couple of days ago, she and Colleen and Anna understand the vexillary case and like also do this like Cauchy-Lustig stuff. Okay. So this is all in terms of some kind of like diagrammatics. You look at diagrams of your partitions or whatever, and Tableau, and we're going to give a sort of different formula. We're going to give a formula for Castelnuovo-Mumford regularity of all matrix Schubert varieties, and it's going to be in terms of sort of a permutation statistic. It's somehow like very analogous to the classical major index statistic. So we call it Rajchgot index. Thanks, Jenna. And the notation is Raj. And so you just compute this permutation statistic on your permutation, and that's the degree of this polynomial. And that means, of course, that if you want to know the regularity of your matrix Schubert variety, you just compute this one permutation statistic, and then you subtract off the Coxeter length of the permutation, this classical permutation statistic called inv. Okay, and the difference is going to be the thing you want. So that's a nice formula. We can actually do better. I cannot tell you not just the degree of the CM polynomial, but I can actually tell you what the leading monomial looks like. If you have sort of a reasonable term order, then, so all of these permutation statistics, they always have sort of vector refinements, right? They have these code versions. So like the code version of Coxeter length, that's called Lamer code. And there's a code version of major index and stuff. So there's a code version of Rajchgot index. And if you just take that vector, the leading monomial of your polynomial is just going to be x1 to the first coordinate of your vector, x2 to the second coordinate, and so on. So you can actually do a little bit better. You can understand what this polynomial looks like. Okay, so let me tell you how to compute this thing. It's really not that bad. So like in my introductory undergrad combinatorics class, we did a lot of permutation statistics, and I snuck this one in with all the other permutation statistics, and no one was fazed by it. It's a perfectly reasonable thing to look at. So let me take my permutation, and I'm going to write it in just one-line notation like this. And I want to compute n numbers, and I'm going to find this vector of length n. So what I'm going to look at is all of the tails of this word. And for each of these tails, I want to find the longest increasing subsequence of that tail, with the special caveat that I'm required to use the very first letter of it. So I use the first letter of that tail, and then I keep going in a way to make the longest increasing subsequence. Okay, and I want to basically record how long that subsequence is. I'm going to get these n lengths. Okay, except I don't exactly want the length, I want sort of the co-length. I'm going to record instead how many things I had to leave out. Okay, so I just get those n numbers and I write them all down, and there's this vector, and that's Rajchgot. Okay, and if I just add up Rajchgot, that's Raj. Just like that's, how these code versions always work. You add them up to get to the statistic. Okay, so here's an example. So I take some permutation. Here's some sort of generic permutation, and I want to compute n numbers. So first, I'm going to start with the 2, and I want to build up maximal, a longest increasing subsequence that uses the 2 and goes on from there. So I could use this 9, but that would be a terrible idea because I'd have to skip everything after 9. So I should skip the 9, not use that. Might as well use 3 and 4. I definitely have to skip 1 because I won't have an increasing sequence if I use 1. Now I could use 7, but if I use 7, I'd have to skip 5 and 6. So better to skip 7, and then I can use 5 and 6. That's more stuff. And then 8's fine. I can use 8. Okay, so what I end up with is this subword. I had to skip 3 things to make it. And so the first coordinate of my Rajchgot is 3. Okay, and now we do the same thing again. We're going to take this tail where we ignore the first part of the word. We're going to start at the 9, and we're going to build up a longest increasing subsequence. Well, if I start with 9, I have to skip everybody after that. So I have to skip all 7 remaining numbers. And so there's my 7 that shows up there. Okay, and then we do it again. Let's take off the first 2 and look at this word. I'll start with the 3. I definitely need to skip the 1. Again, I should skip the 7 so that I can use the 5 and the 6. Okay, so there's my increasing subsequence, and I left out 2 things. Okay, and you just keep going, and you compute these n numbers. They get easier, the words get shorter, and that's my Rajchgot. Okay, that means that with sort of no additional algebra, you get to know the leading monomial of this Castelnuovo-Mumford polynomial. You just say it's going to be x1 to the 3, x2 to the 7, x3 squared, x4 squared, x5, x6 squared. That's going to be my leading monomial. And those numbers add up to 17. So that's the degree. Easy to compute. The Coxeter length of this permutation is 12. 17 minus 12 is 5. So the regularity of the corresponding matrix Schubert variety, the one for this permutation in S9, is just 5. Let's compute that. Okay. Cool. So this solves the problem we're interested in. Let me tell you a few more things about the combinatorics of these polynomials and other things that sort of fall out of the arguments. So I told you before that these polynomials are not going to be, there's not n factorial of them. They're labeled by set partitions. And here's sort of another way to think about extracting Rajchgot that sort of helps you see where the set partitions are showing up. So here I've drawn, here's my permutation, and I've drawn sort of the diagram of it, the graph of it. So 4, 6, 2, 3, 5. Okay, this is my notation for my permutation. And what I've done in this picture is I look at all my dots, and the first thing I'm going to do is I'm going to circle the dots that are maximally southeast. So these are the 2 dots, and we may not do it in blue. These are the 2 dots that are maximally southeast. There's no dot to the southeast of them. Now, if you delete those dots, you can look for what's maximally southeast and what's remaining. Okay, and that's these 2. That's my blob B8. And then if I get rid of those, the things that are now maximally southeast, that's this blob B7, B6, B5. Okay, and so the question of which dots land in which numbered blobs, this is essentially the same information as recording this Rajchgot code. So what you get from this is that the thing that matters is which row indices land inside which numbered blobs. So you'll see, for example, that any other permutation in which the same row numbers end up inside the same blobs, the same numbered blobs, is going to give you the same leading monomial on your Castelnuovo-Mumford polynomial. And in fact, it's going to be better than that. Actually, they're going to have literally the same Castelnuovo-Mumford polynomial, not just one monomial, but the entire thing is going to be the same up to some scalars. So here's this corresponding set partition that falls out of this picture. Maybe you should be using to index things. Okay, so there's going to be set partition many of these, and sort of the best way to think about what's going on here is to think about a double version. So the first thing I want to do is I want to, among all of these polynomials that have the same leading term, they're actually all the same up to scalars, let me pick out a special one and index it by a corresponding set partition. So I have some map that I basically just showed you for taking a permutation and turning it into a set partition. And corresponding to the set partition, let me pick out the special polynomial for it, which we'll call the Rajchgot polynomial, but it's just some particular choice of a CM polynomial. Okay, so there's a double version of all this story. So we didn't talk about them in this talk, but other people, like in Alan's talk, of course, he had double versions of everything. So that you can take a double Grothendieck polynomial. Let me take the top degree piece of a double Grothendieck polynomial. That's going to be some polynomial in x's and in y's. Okay, the definition of double Grothendieck polynomials is basically the same. You have the same recursion down Bruchau order, but just take different initial conditions. Take initial conditions that have both x's and y's, and then recurse down. Well, an interesting thing happens when you strip off the top degree part of a Grothendieck polynomial. It looks like it's sort of a big mess of x's and y's, but it actually turns out the factor as a polynomial only in the x's times a polynomial only in the y's, like this. And the piece in the x's is exactly one of these Rajchgot polynomials, one of these single Castelnuovo-Mumford polynomials. And the piece in the y's is also just another Rajchgot polynomial. It's just the Rajchgot polynomial corresponding to the inverse permutation. That's all it is. And even better, if you pick a sort of a reasonable term order, then I can tell you exactly what the leading term of this double thing is going to be. It's going to be the thing whose exponent vector is Rajchgot in the x's, and in the y's, the exponent vector is Rajchgot of the inverse permutation. So a lot of structure there. And what this means is that if you want to understand what the single Castelnuovo-Mumford polynomial is, like we were doing on the previous slide, I told you before what the leading monomial was. I told you the leading monomial was x to the Rajchgot, but I can tell you what that coefficient on that monomial is. It's exactly a principal specialization of one of these other Rajchgot polynomials, not the Rajchgot polynomial for W, but the Rajchgot polynomial for the inverse permutation. Take the principal specialization of that, and that's going to be the monomial, the coefficient on your monomial popping up here. Okay. All right, so here's a few more funny facts about Rajchgot index. So I told you that this was just some kind of permutation statistic. You might wonder how it relates to the other sort of classical permutation statistics. It turns out it's always bounded below by the number of inversions. That's good because the difference between these two numbers was supposed to be regularity. So if this was not a non-negative number, we'd have negative regularities. That would be sad. So that's good that this happens. You might wonder, when you get equality, you get equality exactly in the dominant case. Easy to see in the dominant case that the degree of the Schubert polynomial and the degree of the Grothendieck polynomial are the same, because the Grothendieck polynomial is a single monomial in that case. So this is some kind of pattern avoidance class, if you haven't seen that before. Okay, you might also wonder how it's related to major index. Well, it's actually always bounded below also by major index. And this is a little less obvious, but you get equality on this class of permutations that we call fireworks permutations. But there's also a pattern avoidance way of thinking about it. It's this, you have to avoid this vincular pattern, 3-1-2, whatever that's supposed to mean. Okay, so some class of permutations. These permutations are counted by Bell numbers. This is another Bell family of objects. Okay, so these are the things where things are very nice. It's the Castelnuovo-Mumford polynomials for fireworks permutations. These are the ones that you want to pick out and name after Jenna. These are the special ones. Okay, well, here's another characterization of Raj. So I told you how to read it off of the words. I showed you how to draw it in a picture and read it off of a picture. Here's a way of recording it just in terms of sort of classical notions for permutations. So if I take my permutation W and I look at everybody sitting below it in right weak order, so this is the partial order on permutations that I showed you before in that picture with the Grothendieck polynomial, the thing with the red lines going down. I look at everything below W in that partial order, and for everything below W, I'll compute Maj. I compute the major index of all of those things. I'm going to get sort of a huge hodgepodge of numbers. There's no real structure in how Maj is distributed. But let me just take the maximum of all those numbers that shows up. That's actually Rajchgot index. Okay, so you can just read it off of knowing how to compute major index, understanding how weak order works. And there's a dual form of this where instead I'll take W again, and instead of looking in right weak order, I'll look in left weak order, which is some sort of isomorphic poset, but in which all the permutations are moved around. It's a different isomorphic poset structure on the same set. And if I look at these different set of permutations sitting under W and this other partial order, and I compute the left major index of all of those things, I get, again, some big hodgepodge of numbers with not a lot of obvious structure. But if you take the maximum that shows up, again, that's another formula for Raj. Okay, so I really like this equality here. This equality seems to be new, as far as I can tell. It doesn't involve sort of any new notions. So this is just some relation among left order, right order, and major index. It's just something very classical, but doesn't seem to have been seen before. And we don't have like a very clean explanation of this. It sort of just falls out of everything we do. Our arguments are like very sort of spirally, and eventually you get to this. But my student, Matthew St. Dennis, seems to have a sort of nice explanation of this particular equality here and a lot more generalities. Those should be forthcoming. Okay, great. Okay, so let me say a little bit about the proof. I have until 10:20, right?
You can even go a bit further.
Oh, okay.
We started a little late, and I think you have until, let me see, 10:20. Yeah,
okay. I'll be fine. Okay, so let me tell you a little bit about the proof. So the proof is a lot of like very delicate combinatorics of the partial orders on permutations and the statistics associated to them. But let me tell you a little sketch of sort of the most interesting piece. So the first thing you want to observe, so I want to prove, I'm not going to show you the proof of all the things I told you. I'm just going to show you how you know that the degree of this Castelnuovo-Mumford polynomial, the degree of the Grothendieck polynomial, how do you know that this equals the Rajchgot index, this funny number that I associated to the permutation? Well, in the case of dominant permutations, it's not so hard to see what's going on. So in the dominant case, the entire Grothendieck polynomial is a single monomial. So the degree of this polynomial is just the degree of that monomial, and it's pretty easy to see what the degree of that monomial is. It's actually just Coxeter length in that case, and it's pretty easy to see that matches up with Raj in that setting. Okay, this is not a hard argument. With a little more work, you can think about what are called layered permutations. So these are things that are parabolic. They're W0 for some parabolic subgroup. Okay, and if you don't like that, there's some kind of pattern avoidance class again. So some nice class of permutations. So here the Grothendieck polynomial is not just a single monomial, but the top degree piece, the Castelnuovo-Mumford polynomial, is really just one monomial. There is just one thing sitting at the top. Okay, and it's not so hard to see what the degree of that thing sitting at the very top is. For example, from the pipe dream formula, you can just draw the pipe dreams for layered permutations and see exactly what it's going to be. And it's not so hard really to check that that's going to just match up with the formula you wrote down for Raj again. Okay. So you have these two cases where you can understand what's going on. Then you want to observe two facts. So, well, the same fact for these two things, and the two things are equal. So not so surprising they should have the same property. But both of these statistics, the Raj and degree of polynomial, both of these statistics are weakly increasing, not just in the right weak order that we had before, or in the left weak order that we had before. They're weakly increasing in two-sided weak order. So by this, I mean, take the union of left and right weak orders. So this is still a weaker notion than the strong Bruja order, but a stronger notion than normal weak order. Okay. I have this thing, and so I have these, both statistics are weakly increasing. So this one here, the fact that these polynomials are weakly increasing, you can sort of pull this off of the divided difference recursive construction that we had for these things. You can see that those have to be weakly increasing as you go up. And the fact that this one is weakly increasing, you can get that. It's hard to see that from the original definition I gave you, but you can see it from the characterization we had on the previous page, where it was a maximum of major index over some interval. If it's a maximum over the interval, then it can only go up as I make my interval bigger. Okay. So I have these two things. They're both weakly increasing. And now what we do is we do basically a squeeze theorem. So what I've got, here's my W that I'm interested in. What I'm going to do is I'm going to find below it something layered. There's something sitting below in two-sided order. And I'm going to find something sitting above it that's dominant. And I'm going to do this in such a way that the two things I found that are sandwiching my W, they have the same Rajchgot index of the thing I started with. So you can do this basically from that blob diagram that I drew, and shoving the blobs around in clever ways, you can move it to the right sort of thing here. So I'm going to find something layered where they all have the same Rajchgot index. So Raj is going to be R, Raj is going to be R, Raj is going to be R in all of these cases. In the layered case, I know that this is also equal to the degree of my polynomial. In the dominant case, I know that this is also equal to the degree of my polynomial. And yet, the degree of my polynomial was supposed to be weakly increasing all the way along my interval. And yet it didn't change from down here to up here. So by a sort of squeeze theorem, it was actually constant on the entire interval. And so in particular, it had to be the same right in here. Okay. So you get this sort of weird, weird facts about two-sided weak order, about sort of various permutation classes and how they arrange themselves around each other in weak order. And out of that, you're able to sort of squeeze the things that you need. Okay, great. So here again is our final picture. So what we want to notice is, again, we had this thing here and we had this thing here, and they were the same. And so how can we compute this? Well, I told you I was supposed to compute the Raj code of these two permutations. So here, my Raj code is going to be what I get from starting at this first letter. To get this one here, I need to leave off the 1 to make a strictly increasing sequence. So my Raj code is going to be 1. And then from the 3, I need to again leave off the 1. So it's going to be 1, 1, 0. There's my Raj code. Over here, my Raj code, starting with the 1, I can use the 1 and then I'm going to leave out either the 2 or the 3. Right, I have a choice on which one to leave out, but either way, I have to leave out one thing. So I get this 1. And then from the second coordinate, starting with the 3, I definitely have to leave out the 2 after that. There's my 1 again. And then starting at the end, I don't have to leave out anything. And so you can see now from this definition I gave you, I'm getting the same Rajchgot in these 2 places. And that's exactly why I'm getting the same monomial on these 2 things. I'm getting x1, x2 in both cases to match these ones here. That's actually all that was going on. All right, great. I will stop there. Thank you.
Thank you. It was a very interesting talk. Do we have any questions?
Maybe I have a question. Oh,
okay. Go ahead.
Which one?
Francois, I don't see anybody else.
Okay. I can't, my camera is not working, so sorry. This, you had a picture where you were, you had the graph of a permutation, and you were doing these. Yeah, that one. This is strongly reminiscent of Vienno's shadow construction.
Yeah.
In the for RSK. So do you think that there is something similar going on here, where you could get more information than just only the leading degree maybe, but also the rest of the structure of the polynomial by looking at the similar peeling off of shadows like Vienno does?
So we did think about how this related to RSK, and we didn't really understand how to make sense of that.
Okay.
We also don't know how to extract all the other coefficients of the polynomial in a nice way. Right? There's even sort of an obvious one. Because here's a sort of related question: is like, suppose I tell you what the degree of this polynomial is supposed to be, can you go and write down a pipe dream to realize that? In fact, it's quite difficult. We don't know like a nice algorithm for constructing witnesses in general. So I think there's a lot more combinatorics to work out. Like this picture is like extremely helpful, but you can presumably do more with it. Right? There's more structure to these polynomials than we're able to handle.
So the other thing is, whenever I see Madge and Inv coming up, I think that this is like a shadow, maybe, but comes from the descent algebra structure behind. So maybe Raj has a nice link to the descent, the structure of the descent algebra.
Yeah, that's the thing I don't know very much about at all. So yeah, I'm not at all sure. That's a good point.
But if you would find such a link, then you would have nice ways of going to other Coxeter groups. And so, by the way, do you have anything similar for other Coxeter groups?
We don't. There's a few obstacles. So the first obstacle is it's not clear what you're doing in terms of regularity when you work with other Coxeter groups. But even if you did do that, it's not entirely clear what your analog of a Grothendieck polynomial is. I mean, I guess people have these things in like classical types, but it's not quite clear what that's computing for you. And I'm not exactly sure what the correct definition of Raj is in that context.
Thank you.
Yeah.
Nantel asked, and maybe kind of answered it in the last response. If we go back to pipe dream, do you get more information about them for the CM polynomial then?
More information about the pipe dreams. No, I wouldn't say we like really learn very much about the pipe dreams. We do have to use the pipe dreams at some places in the proof. So in the proof, we're sometimes using the characterization in terms of divided differences and sometimes the pipe dream definition. But I don't feel like I learned very much about pipe dreams from this. Like I still can't actually construct the pipe dreams that realize the degrees that I say things have in like a systematic way.
And Andrew Wilson says, you mentioned RSK, so there's no simple relationship between this code and statistic and RSK shape?
Not that I know. I mean, maybe I missed something, but I don't know how to extract anything out of RSK.
Okay.
But like morally, it does feel like very similar. Like I agree that like something's going on.
If that's all,
Question?
I've got one more question.
Go ahead.
Okay. You mentioned layered permutations at some point. My question is it true that for them the CM polynomial is just a monomial?
Yeah.
Okay, and can you characterize such situations a part of the dominant and layered permutations? Or speaking more generally, do you know how many monomials does a CM polynomial have?
In general, so in general, I don't exactly. So when is it a single thing? Well, it's a single thing. Okay, so I'll tell you these. These Rajchgot polynomials. When are these single monomials? These are single monomials basically in the case of you're going to get one for every dominant.
Okay.
So the other ones that are single monomials is because somehow the blob diagram for that permutation looks like the blob diagram of something dominant. Is I guess the way to say that. In general, the question of how many monomials does it have? Well, that's the question of this principal specialization that shows up here.
Yeah.
So you can, supposing you can compute just the leading term of one of these polynomials, the coefficient of that is going to tell you the number of monomials and the one for the inverse permutation. So like in some sense, you have some handle on that information, but I don't have like a nice formula.
I see. Thank you.
Not like a McDonald identity for principal specialization.
Okay, so I'll ask that other questions get asked offline. And let's thank the speaker again. So just to give ourselves a little more time, I'm going to suggest that we restart at